All right, if not, let's get started then. So today we're going to talk about autoencoders. So, yeah, I mean, the reason that we start with autoencoders is really simple, and the objective is also simple. It's just compression and then decompression. So it's basically a way to reduce your dimensionality of your input. And we can extend this to a variational autoencoder in the next class. So it'll be a good starting point. And today's topic is latent representation. So we're going to talk about latent representation and then move on to autoencoders. Then I felt like some of the people who attend this class have never really properly trained a neural network or any machine learning model before. So it's kind of like a fresh start for them. So I thought it might be a good idea to actually go step by step what we want to do in training our neural network. So it doesn't really just apply for autoencoders. It applies for any neural network. So if you want to train a neural network, what is your loop? What does your loop look like? So we're going to talk about that for a bit. Because I felt like in the last practice, we kind of moved on pretty hastily. So we didn't really go line by line when we were training stuff and when we were loading up the MNIST images and then calling the optimizer and all that. I thought we didn't really talk about the details, so I'm going to spend some time on that. And then visualization. So when we learn the latent representation using autoencoders, we want to visualize it. We want to scatter plot it on a 2D plane to see how the learned latent representations are doing in the lower dimensional space. After that, we're going to talk about autoencoder variants, basically just two very representative variants, which are denoising autoencoders and sparse autoencoders. Okay. All right, so latent representation. So remember that we used NLP, or feed forward neural network, with a single hidden layer to classify a given image into a man or a woman. So it's a binary classification. Just a reminder. And I think I briefly mentioned that this 4-dimensional hidden layer is actually a latent representation of your image vector. So why that is so this is our original input, which is x, and this is our h, which is a hidden layer. And we could see that we could interpret this line as a logistic regression as well. So it's a logistic. So during this process, what we're doing is we're just reducing the dimensionality of your input and then projecting it into a 4-dimensional space. Originally, it was a 784. Is it? Yeah. So yeah. Okay. So it's 784 dimensional space, and we're reducing it, or we're mapping it to a lower dimensional 4-dimensional space. And with that 4-dimensional input, we are doing logistic regression or binary classification. So this is actually another input in this logistic regression. So we can think of having a 4-dimensional input. So 4-dimensional input, I'm calling this a latent representation because we actually don't. What we really see in the real world is this 4-dimensional X, but this is something hidden from us. We can't really see what it looks like, or we can't actually properly interpret what it looks like. I mean, we conjectured that maybe the first dimension might be distinguishing if the image has long hair or not, and the second dimension would be we're just imagining. Second dimension might be responsible for mustache detection, and the third dimension might be responsible for ribbon detection and all that. But it's not really a guarantee that it'll be as interpretable as this example. So it's a latent representation, and so if it's a mapping between 784 dimension to a 4-dimensional space, then we can assume that the above female image might be mapped to some specific value, 0.8, 0.1, some value, some latent 4-dimensional value, and the bottom image of a man might be mapped to another 4-dimensional value. So it's a function that maps between 784 and 4-dimensional space. And I just want to say, is it a linear transformation or a nonlinear transformation? what we saw here, this process of mapping your X to H, is it a linear transformation or is it a nonlinear transformation? 혹시 아시는 분 계신가요?
액티베이션 펑션.
그렇죠. 액티베이션 펑션이 시그모이드였죠, 여기서. 저번 수업에서. 그러니까 nonlinear transformation이죠. Yeah. So it's a nonlinear transformation. 대답 안 하시지만 다 알고 계시는 거죠? 그렇죠. 그렇게 믿고 싶습니다. Yeah, a lot of a lot of takers in the chat. Nice. All right. Yeah, it's a nonlinear transformation because we were using sigmoid activation function here. So it's a nonlinear transformation. So it's if you remember what you've learned in the middle school, like when you very first time were learning the concept of function, there was a set to set mapping. So original space being the domain. This is the domain. Or in Korean it would be 정의역. And what the space that the elements in the domain is being mapped to is codomain, which is 공역. Then the actual mapped elements in the codomain are the set of them are called it's a range. So in Korean it would be 치역, right? So please, it's like nothing really new. It's just refreshing your mind on what you've learned like maybe 10 years or 15 years. So here, this mapping or this transformation is what the hidden layer was doing. So if this is your neural network, then this part is what is responsible for this transformation or mapping. So like each individual element or each individual image in the 784 dimensional space, it will be mapped to not necessarily a unique element in the latent space, because there's a guarantee that they will all be mapped to an exactly unique element in the latent space or the codomain. There might be some image that is mapped to exactly the same same element in the codomain or in the range. 그러니까 이 똑같은 옷에 맵핑될 수 있잖아요. 그러니까 이게 이제 1대1이 아닌 거죠. So it's not a one-to-one relationship. It's not guaranteed that it's a one-to-one relationship. I mean, it's, most likely it'll be a one-to-one, but there's never really a guarantee. So, and you can see what kind of, if the how it is transformed or how it is mapped it depends on your network, what you want your network to do. So yeah, if it's a four-dimensional space, and especially in our case, because this was our image of X, and this is being mapped to four-dimensional hidden layer, and then is mapped to a single scalar output, a probability, and we were using a sigmoid activation function here, so it was all sigmoid. So we can think of, we'll just take three first dimensional, because we can't really visualize four-dimensional space. So taking the first three dimensions and then visualizing it using a Euclidean space or like Cartesian coordinate, then this will be 0, 1, 0, 1, 1. And so the maximum value that any element can take in this latent space is 1, because we were using sigmoid activation function. So the outcome of the activation function is 0 to 1. So you can imagine that all elements in your four-dimensional space, all elements, like any image that is mapped to four-dimensional space, lives inside this cube. And it'll be actually a hypercube because it's four-dimensional space. So if we still like imagine, we're imagining things. Is someone? All right. Okay. So somebody's didn't turn off their mics. All right. I just muted everybody. Okay. So continuing. So as I was saying, if we're still imagining things, then the first dimension or first axis in your Cartesian coordinate, Cartesian space would be long hair and mustache and ribbon, and then there will be a like fourth axis that we cannot visualize in this, in this 3D world, which will be makeup. And then all the elements in your four-dimensional space will live inside this hypercube. So it's a very compressed space because originally your input was 784 dimensional space with, well, I mean, you probably normalize it between, so your images would be normalized to values between 0 and 1 anyway. So it was a really gigantic hypercube in the beginning. So all the images that you normalize would be living inside a 784 dimensional hypercube, and then you are compressing it all the way down to 4-dimensional space. So it is way more compact than before. All right. So how do we learn this space? How did we learn to transform, map between the original space and the 4-dimensional space? We did it by minimizing the cross-entropy loss. In our original example, in our man-woman binary classification scenario, what we did, we didn't explicitly learn the 4-dimensional space. We just, we defined that there should be 4 hidden neurons in your feed-forward neural network, and then we just backpropped it. We trained it by backpropagation. And the criterion or the objective was that we wanted to classify an image into a man or woman correctly as many times as possible. So that is how everything is shaped implicitly. We just, we use the loss function, cross-entropy loss, and then we backprop from the top all the way to the bottom. So your space, or your 4-dimensional space, will be shaped in a manner that facilitates, or it makes easy for the model to distinguish between man images and women images. So there's a very nice, visualization from some website called cola github.io. So obviously it is not moving right now. So let me just try to show you guys how it looks like. Or you guys can actually click it yourself and see how it. Open. Yep. Right. So, yep, here, right here. So, actually, yeah, we want to see it from the very beginning. Okay, I can't control it. All right, so yeah. Here, originally the space was just like a checkerboard. It was a grid line, and then you're distorting, or you're scaling, or you're expanding or shrinking your grid board, and then so here you're actually kind of rotating your grid line, and then you're moving it horizontally, and then what's happening is now you are distorting it. So this part is the linear transformation. Linear transformation using a matrix can rotate your space, and it can shrink or expand your space, and then distorting it like this, it is a role of nonlinear activation. So maybe it was using a sigmoid function, so that is why it's distorting your original space into like S-shaped space. And what you really want to do is, if you want to classify between the red lines and the blue lines, you need to do something like this. Yeah, it would have been nice if I could pause this for a while. Right here. So originally your space looked like this. Okay, can I? All right, I can. I can use. All right, and yeah, just I want to actually. Yeah, so this is your starting point. So you have a 2-dimensional space and all your red lines, and so this is a single class. So all your inputs will lie on this line like this, and then another set of inputs resides on this line, on this kind of spiral-looking thing. And then you want to classify between the red elements and the blue elements. And with a linear classifier. There's no way that you can do this. If you draw a line like this, then you are missing, like, maybe this part is your error and this part is your error, because you want this part to be all blue and this part to be all red. And there's no way that you can draw like a nice line, a linear line that can separate these two classes like perfectly. So you want to draw something like this, actually. So we need to draw a line like this, which is very, very nonlinear. So this is the only way that you can like cleanly separate between the red class and the blue class. And the way that you can do it is by using nonlinear transformation. So first here, it was like compressing in like diagonally, so that was linear transformation, and then you're warping it, you're distorting your space using nonlinear activation, and then you're repeating the process again and again and again until you can draw a line very cleanly between the red region and the blue region. So here, so it's a repetition of linear transformation, then nonlinear activation, another linear transformation, and then nonlinear activation, another linear transformation. So you do it until your space is so distorted that it is easy for your model to draw a linear line between red region and the blue region, so that the accuracy is 100%. Yeah. All right. So this is what happens to your latent space when you learn to. So obviously the criterion or the objective here is probably cross-entropy loss. And you're doing binary classification between the red dots and the blue dots. And if you do it, and this is probably using like 3 hidden layers, because you can see that about 3 times your space is linear transformed and nonlinear and distorted, and then linear transformed and another time distorted. And then, like, I think you can see 3 repetition of that. So probably using 3 hidden layers, and then at the end, it is so distorted that you can draw a linear line to perfectly distinguish between the two. So this is what happens to your latent, or this is how you learn your latent space. You don't explicitly say what kind of latent space that you want to learn, but it is learned by backpropagation from the top. Right. So at the end, it looks something like this. All the blue things like live here, and the old red things live here, and then you can just draw a line like this, which is a perfect distinction between the two. And, I mean, you can imagine that if you distort your space too much, then it'll overfit, because you're distorting your space in such a weird manner that it won't generalize to test cases. So you don't want to do that. You can like get that kind of intuition by just looking at this visualization. Right? Any question until here? So this is a bit more related to linear algebra rather than neural networks, but they have a very close relationship between the two, like manifold learning and neural networks and linear algebra and all that. They are all tightly connected. All right, moving on. So yeah, your latent space is shaped by your loss function or your task, and then there can be, there are infinite number of tasks. But you can basically, imagine that if you're doing man-woman classification, then your latent space is shaped in a manner that facilitates classification. If you're doing iris classification, it's the same manner. If you're doing word embedding or maybe even French-English translation, then you are warping your text space or natural text space in a manner that facilitates French to English mapping, right? So I mean, it's hard to imagine, but it's the same principle. So there's like a space of your French words, French sentences, then there's a space of English sentences, and you want to map certain elements into here. Like this could be je, suis, étudiant, which should be mapped to I am a student. Right? This is it. So this is what you want to this function, this mapping function is what you want to learn when you're training your French-English translation. And it's really extremely hard to learn this function properly. So you are warping, or you are learning your space to the degree that this f function is easy to learn. And these days, people use transformers to do that. So transformer, you can, I mean, a simple like feed-forward neural network that looks like this was already warping the space quite a bit. But if you think about transformers, it's a way more complex function compared to just feed-forward neural network. And it's really hard to imagine what kind of things are happening to the latent space when you're using transformers. But anyway, it will probably be like really highly nonlinear compression and decompression and, like space manipulation. Okay, so some questions? 저렇게 2D 스페이스 모욕되는 건 액티베이션 펑션 때문인 건가요? 네, 맞습니다. 그 non-linear activation 펑션 때문에 그런 거예요. 정확히 말씀드리자면. 리니어 트랜스포메이션을 할 수 있는 거는 스페이스를 확장하는 거. 그러니까 이제 예를 들어서 이렇게 생긴 거를 뭐 이런 식으로 X축으로 확장한다던가 뭐 반대로 Y축으로 확장한다던가 아니면 I'm sorry. So yeah, the only thing that you can do with linear transformation is either you expand along the certain axis, maybe both axes, like X and Y, or maybe you can shrink or compress along your axes. You can rotate your space, like this, by using a sine and cosine functions properly in your matrix, in your transformation matrix. And if you use bias terms, so this is like this here is what Wx, this is Wx, this will be like W to W1. If you use Wx plus B, then you can push your space to a certain direction. Like now this is not a really good drawing. Yeah, yellow is not a good color. If this was your original grid line, then if you use plus B, like along the y-axis maybe, if you use a, then it will look like maybe you can push the entire thing down like here. Here, like this. So like you're like scaling, not really scaling. I don't know how to put it. Like you're moving your grid line along your 2D plane, so you can push it upward, downward, push it right, push it to the right, push it to the left. So that is what B does. If you don't use the bias term, then all it can do is actually your entire thing is fixed to the origin, to the origin, which is 0, 0. It'll be fixed, and then you can rotate, or you can shrink, or you can like compress, but it'll still be fixed to your 0, 0 original point. So when you use bias term, that's when you can actually move your grid line along, like in a lot of different directions. And if you use nonlinear activation, then that's when your space becomes like distorted. And depending on what kind of activation function you use, it'll be differently distorted. If you use ReLU, it'll be like all your negative values will be like zeroed out. And if you use sigmoid or tanh, it'll be more like like a sinusoidal shape. Is there any relationship between classifying lines getting linear and overfitting? Your classifying line will always be linear in the end, because no matter how many layers that you use, it'll like until right before. So this is your final logistic regression, like module in your multi-layer feed-forward neural network, and all your model does until this point, like here. All it does is just learning the space or mapping your input to a lower dimensional space. I mean, it doesn't have to necessarily be a lower dimensional space. Doesn't matter. Anyway, so it's basically transforming your input and putting it to some another dimension and distorting it, and you repeat it until the very last component, which is basically a logistic regression component. And then that's when you draw a line. And what I was saying before is that if you distort your your space to the extent that it is like perfect, like your training samples are perfectly classifiable or distinguishable, then it's probably you've gone too much. You like when you get like 100% training accuracy on your training samples, then it's more or less likely that you are overfitting. Your model's overfitting, and that's because you have distorted your space too much, so it doesn't generalize. 2D we're going to is it like PCA, but PCA is for linear transformation. Yeah, so we're going to talk about PCA today. So we're going to make a comparison between PCA and autoencoders. So let me just, well, PCA is one way to reduce your dimensionality, but your neural network doesn't necessarily need to reduce. It can actually right. So this is your 784 dimensional input, and it can be like 1,000 dimensional hidden layer, and then output. So it doesn't. I mean, the space, the size of the space, and the structure of your neural network totally depends on your design. There's no rule that dictates that your hidden layer must be smaller than your input size dimension. There's no rule saying that. So it doesn't really matter. If you use 1,000 dimensional space, then you're actually expanding or you're projecting your input to an even larger dimensional space. Not sure if that's a good idea. I mean, yeah, there's no as long as it works, it's fine. As long as your model has a good generalization performance, then it doesn't really matter what kind of choice you make. So yeah, so the reason I came up with this is because PCA is usually used for dimensional reduction. So you want to reduce your 784 dimensional input into like 100 dimensions or 5 dimensions or 2 dimensions. That's when you use PCA. And here we're not in this scenario we're not reducing the space. We're actually like expanding the space. So there's this kind of like PCA and the direct comparison between PCA and this kind of neural network doesn't really make a lot of sense. What is manifold learning? Could you explain it again? Manifold, basically, then we need to get into the definition of manifold, which is I'm not an expert in. So I should probably really go deep into it. But basically, you're assuming that like your space, your original input or raw input of 784 dimensional inputs live in a very weird, highly non-linear space, but locally it might look like a linear space, something like that. And then you want to map your input, and you want to map your original inputs to a locally linear space. I mean, it's really hard to explain. For example, Swiss roll is a very typical example that people use in manifold learning. Actually, let me take a look at it. Oh, this was better. Yeah, maybe this is a good example. Yep. So yeah, this is kind of hard too. Oh, here it is. Yeah. All right, this is really giving me a hard time. All right, okay. So if you imagine that your three-dimensional input, this is a three-dimensional space. There's okay, I can't sketch here, but you get the things in number 2 and number 1. They are three-dimensional space, and your inputs are it is located in a very nonlinear manner. It's like a Swiss roll. The Swiss roll is like a bread. So It is. There's no way that you can draw a linear line to do anything here because it is so like it looks like a spiral. But they look linear, like locally. The blue dots here, the dark blue dots here. If you look in a very direct neighborhood of a single blue dot, then its neighbors can be seen as living inside a linear plane. Like you can imagine doing like a Taylor expansion type of thing. So locally, your neighbors, yourself and your neighborhood lives in a linear plane. So you can apply that principle in all samples, like going through all the all those samples in your Swiss roll type looking shape here, and then you can roll it out, and then which looks like number 4. So because locally they will be living inside a linear plane, so you can do that same. You can apply the same principle until you see until you can unroll your Swiss roll into a long linear plane it looks like in number 4, and you can then visualize, or you can do classification. You can do clustering on top of the linear plane because linear planes are easier to manipulate than this highly complex nonlinear plane. I think this is kind of a motivating example, and the theoretical background and the foundation of it is probably too complex, and I don't have a really deep understanding of it. Is there any specific reason why mostly people prefer value over sigmoid? That's because actually we might be able to. Okay, maybe this Thursday we might be able to test both activation functions when we are implementing autoencoder. Usually, values let your model train way faster than using sigmoid functions. So sigmoid functions it takes longer to train basically, and that's especially the case when you use a lot of layers in here. If you're using 100-layer ResNet, 100-layer convolutional neural networks, then using a sigmoid function is a very bad idea. It probably doesn't train as well as using, or maybe it doesn't train at all. But if you use value function, then yeah, it trains way faster. Okay, moving on. Right. So yeah. So since the class today, the topic of today's class is autoencoders. That is when autoencoders are used for compression usually. I mean, it's not necessarily always compression, but it's a good motivating example. So as I said, your latent space is learned depending on your task or your loss function. And when you want to do image compression, then your space will be manipulated or learned in a manner that facilitates or makes it easy for your model to compress your image and then reconstruct it without any errors. All right, so moving on to autoencoders. All right, so autoencoders consist of encoder and decoder. So people who are familiar with translation, machine translation, like seek-to-seek model, there is a encoder and decoder. It's the same principle. There's encoding module and then there's a decoding module. And the latent representation or the bottleneck here, because this is 704 dimensional, this is 704 dimensional. This is 4-dimensional. So you're compressing your input into 4-dimensional space. So this is your bottleneck, and compressing or mapping to a lower dimensional space is encoding, and then decoding is basically decompression. And you call this latent representation sometimes code. So this here is a code for your raw input, and then it is sometimes called latent variables, or sometimes in neural networks it's usually called latent representation or hidden representation. And this kind of terminology, like encoding, decoding code, this comes from communication theory. If you are familiar with Shannon theory and that kind of stuff, and capacity and entropy of your communication protocol and all that. So these encoding, decoding, this kind of terminology comes from that field. Right. So, I mean, this is mostly it. Autoencoders are really simple neural networks for compression usually. So this is. I hope that you can imagine how you want to implement your, if I were to, tell you or ask you to implement an autoencoder that can compress your 784 dimensional image into like maybe 10 dimensional space, I hope you can imagine how you would code in PyTorch and how to do it, because it's a really simple network. So like this is the essence of today's class, and the rest are just elaboration. Right. So as I said, consists of encoders and decoders, and you can compose your encoder and decoder using a single nonlinear neural network, and that's it. So your input is an x, your hidden code is z, and your reconstructed output is x prime. And the way that you can compress is just simply using a nonlinear neural network once. There's just one single nonlinear layer, and that's it. So W1x plus B1, and f being some sigmoid function or tanh. So this could be anything. This could be sigmoid, or it could be tanh. It could be ReLU. It doesn't really matter. It's up to you, and up to your task basically. What kind of latent representation that you want to learn, and then once you've learned it, you need to decompress it. So taking z, you do W2z plus b, and then using some another nonlinear integration function, and then you get x prime. So and you probably want your x and x prime to be the same as much as possible because it's reconstruction. So your loss should be, so this is encoding, this is decoding. What kind of loss should we use to train your autoencoder or shape your 4-dimensional latent space? What will be your first choice? 뭘 써야 될까요? loss function. cross entropy? 네, 그렇죠. MSE. Yep, there is also 준민호. Yep, MSE. I mean, it might be confusing because in this example I'm using 0, 1, 0, 1 here, so you might want to say like cross entropy loss, but this is actually my fault because usually your input doesn't have binary values. It has a continuous value, so it'll be like 0.1, 0.2, 0.8, minus 1.7, something like that. A lot of values here, and then you want your output to be x prime 1, x prime 2, x prime 3, x prime 4, and you want x prime 1 to be the same value as 0.1. You want your x prime 2 to have the same value as 0.2. Something like there should be a one-to-one match between your x and your x prime. And the way you can force that to happen is using mean squared error. Yeah, negative log likelihood is usually used for classification, but here you're more or less doing regression actually. I mean that is more general. So MSE, or I'm not sure if people use mean absolute error, but I think mean squared error is your way to go. Right, so if you use it in a mathematical notation, it's basically just L2 norm squared. You want your x and x prime, the difference between x and x prime to be as minimal as possible, which is squared error. And then you don't just have one image, you have a batch of images, right? So you're doing mini batch update. So it should be actually n 1 over n plus xi negative xi prime 2. This would be n. So this is your loss function. And then you want to train your loss function. So this will be your loss x prime. This should be actually, this should be a matrix actually. So yeah, x and x prime should be a matrix because we're dealing with mini batch here. I mean, we're assuming that we're dealing with mini batch. And then once you have the loss, you can call loss dot backward and then do optimization step, and that's how you train your neural network. Right? Really simple, right? There is nothing too difficult here. And you can even use like multiple layers. So there's no rule that you must use a single nonlinear layer. You can use like 2 nonlinear layers. So this is an example. You have a intermediate layer H, and then you have another intermediate layer in the decompression phase as well, which is H prime. So you can go even like crazy as using like 100 nonlinear neural network layers in the compression stage and decompression stage. Although I don't really see the point why you would do that. But you can imagine that if you can remember what you've seen in the Cola GitHub.io, what you were manipulating your space to facilitate classification. So using many hidden layers probably is like adding more power to your model. So if you remember the overfitting, underfitting principle, adding more power to your model leads to overfitting, right? And adding more layers to your neural network is adding more power to your network because it is giving the model a freedom or option to further distort your space, right? So in this case, if you imagine using many hidden layers in your compression stage, then you're distorting your space really like as many times as your number of hidden layers, and then finally you're projecting it to like the space that you really want, which is the Z space. So if your input X is really complicated, it's not just like 700. Maybe you can imagine your X being like 100 million dimensional input, maybe or like 10 million dimensional input. Then using a single neural network to map to a lower dimensional space is probably not a good idea because your original input space is too large. So you want to break down into several like intermediate steps. Maybe that's when you want to use 10 hidden layers or maybe 20 hidden layers. But in this case, when you're dealing with a 784 dimensional input, which is basically MNIST image, then you probably don't need 10 hidden layers or something like that. Like probably 1 or 2 hidden layers is just fine. Or maybe even just 1 hidden layer is also fine. You can try that out on this Thursday. All right. The activation function f is the same both for encoding and decoding. Oh, that's an interesting question. I always assume for no reason that it should be the same linear activation function. But I guess it doesn't have to be. I mean, in the final layer, there's a, like, if your input was, if your input, all your values in your input space was between 0 and 1, then you want your final somewhere, if there's like a lot of hidden layers here and here, then you want your final f to be sigmoid because your original space was, the values in your original space was 0 to 1. So you want your output space to have 0 to 1 so that you can calculate x and x prime properly to facilitate better reconstruction. But in the intermediate layers, like here and here, I don't think there's a reason that you have to use the same sigmoid function all over, like all the time. You can probably use ReLUs in the intermediate layers, but in the final layer, you need to be careful because you want your reconstruction to have the same value as your original image. But other than that, I'm not sure if there's like a strict rule that all the f's or all the nonlinear activation functions in your autoencoders should have the same form. I don't think there's a reason to do that. You can try that out this Thursday as well. 인코드와 디코드 동일한 형태를 갖는 게 좋나요? That's also an interesting question. It is a rule of thumb that the power of your encoder and the power of your decoder should be the same, because if you use certain amount of power in compressing your image into a lower dimensional space, then you probably need the same amount of power to map it back to the original space. But this is just rule of thumb. For example, zero x. X prime. For example, if you use 2 hidden layers between your input and the latent space, and it just so happens that it didn't really need that. So there's this is H1, H2, so it'll be mapped to a lower dimensional space, incrementally, and then it'll be mapped to the Z space. And let me actually draw one more layer here. Assuming that you use one more layer in your decompression phase, if your decompression phase, I mean, obviously you're giving more power to your decoder than you gave to your encoder. So theoretically, at some point, your decoder will. So there's like matrices here. There's matrix 1, matrix 2, matrix 3, matrix 4. At some point, your one of the matrices in W2, either W2, W3, or W4, will be learning an identity matrix because it doesn't really need that power. Because you're giving one extra layer to your decoder, which is unnecessary because when you're encoding, you use only 2 hidden layers, but in the decoding, you're using 3 hidden layers, which is H1 prime, H2 prime, H3 prime, and you don't really need that kind of power. So theoretically, it might be the case that one of the W2 or W3, W4 is an identity matrix because it doesn't. Nothing needs to happen in that step. So in the same principle, I don't really think that it really matters whether you use the same number of layers in your encoder or decoder. But the rule of thumb is probably want to match the power between the encoder and decoder. X를 인코딩 시키기 전에 0일 사이로 만들어주는 게 학습에서 도움이 되나요? That relates to scaling. I have enough time. Basically, if your original input has values like, let's say this is your x, and it is 4-dimensional, and the first dimension, the value is like 10,000, and then the next dimension, the value is 0.002, and then again, like this is 10, this is like minus 1 million. If your input looks like this, then if your input looks like this, and you want to do certain type of test, like classification or regression, using this kind of input, then your hidden layers in your neural network needs to learn a very extreme weight values, because the first dimension is like 10,000, and like the last dimension is minus 1 million, but intermediate one's like 0.00 something. So there's like orders of magnitude difference between the dimensions. So your weight matrices in your neural network needs to adapt to it, which is just extreme values. So you don't want that to happen. It'll really make your training phase difficult. So that's why you want to normalize it to either like 0 to 1, or maybe negative 1 to 1, or some range to your liking. Basically, this will make your training process way faster than using the original values like this. All right, I hope that answers your question. Moving on. Yeah, so before in our example, we were assuming that the hidden layers, or each dimension in your hidden layer or hidden space, would be responsible for something like long hair or mustache or ribbon or makeup. But in this case, would that still be the case? Because before, we were using man-woman binary classification to learn the latent space. But here, the objective is different. So probably not. Probably they use a very different latent space compared to your feed-forward neural network example in before. So basically, this is just compression. So this is dimension reduction algorithm. And if you think about what PCA does, if you're familiar with PCA, or if you're not familiar with PCA, just a very simple introduction is that if your data set looks like this, so it's a 2-dimensional data. Your data set resides in a 2-dimensional space, and it looks like this. So it looks like an ellipse, 타원형이. So it's just distributed along the 2-dimensional Gaussian distribution, and you can see that one side is like longer than the other side. So the best way to represent, or the best way to describe this data set all these dots is actually using an axis or a basis. If you think about linear algebra, finding a basis that maximizes the variance between your input samples. So that is what PCA does. So there's X, I mean, anything could be a basis. I mean, this is two-dimensional space, so like 1, 0, and 0, 1 could be your basis. Like 1, -1, 2, 2, comma 0. This could be your basis. Anything like there's infinite number of bases in your two-dimensional space that can span your two-dimensional space. But you want to learn a orthogonal basis. So this is all linear algebra. So you want to learn an orthogonal basis that maximizes the variance between your samples, which is one basis goes this way, which is like the longer side of your ellipse, and on the second basis should be orthogonal to the first one, so it has to be like this one. So that is your PCA. If you think about this vector here doesn't really have a meaning. So originally, if it was your two-dimensional space, then this could have been long here, or no, this is not a good example. Let me rephrase that. So. If it's your housing price data set, then this is your house's location, and this is the size of your house. And then this is input sample 1, 2, 3, 4. It could be in Seoul. This is Daejeon. And then the size is like Pyeongsu, so it's like 30, 40, 50, something like that. And so this axis could be, this is also not, I'm sorry, this is also not, this is categorical variable. Making a lot of mistakes here, I'm sorry about that. Let's say the floor. So Chungsu, so 10층, 15, 12. So this is your floor dimension, this is your size dimension. And your data set looks like this, or in the two-dimensional space where the axes are floor and size, that your data set might have been scattered like this, like in a along like following a two-dimensional Gaussian space, and you happen to do PCA, you apply PCA on that data set, and you find this basis, then the semantic or the meaning of this basis probably not that interpretable, because the basis here is no longer like clear. It's no longer disentangled between size and floor. So it's some hidden meaning. There could be some hidden meaning in your PCA basis, but it's really hard for people to or humans to understand what it really means. Same principle could be applied here. Like if you do a dimension reduction to maximize the reconstruction performance, then it is probably very likely that these hidden dimensions won't be too interpretable. I mean, there's probably a way to force interpretability or disentangled representation. But if you just use vanilla autoencoder, then your lower dimensional space won't really make a lot of sense. All right, so autoencoders versus PCA. So they have the same objective, which is minimizing. I'm sorry, this is minimizing reconstruction error. Yeah, both PCA and autoencoders, their objectives are the same. It's minimizing reconstruction error, which is the same as maximizing the variance between your input samples. So they are actually the same thing. But the way that PCA and autoencoder achieves that goal is very different. So PCA actually really use variance to maximize reconstruction performance. And the way it does is it's basically you apply singular value decomposition on your covariance matrix. So if your input looks like this is your X, and this is a sample 1, sample 2, sample 3. This is your feature 1. Like this is feature 1, feature 2, feature 3. If this, I'm sorry, this is probably not a. I have to think of this is your X1, X2 first sample, second sample, third sample. If your X looks like this, then you do X transpose, and then, or was it X transpose X? Doesn't really matter. X transpose X or X transpose, and then this becomes your covariance matrix, assuming that it is normalized, and then you apply singular SVD, singular value decomposition, on top of this this covariance matrix, then you get then you get like a variance maximizing basis of your covariance matrix. So yeah, it's selecting K, which is up to your choice. Like if your original input was 784, then your K could be 10, 20, 30, 100, doesn't really matter. Like it depends on how much you want to compress your input. You're selecting K variance maximizing bases, and the principle or the assumption behind that is you can ignore small variance. So small variance in your data doesn't really matter or doesn't really help when describing your data set. So you want to throw that away, and then you only want to take the top maybe 10 variance maximizing bases. And autoencoders don't really have that kind of principle. It just uses very nonlinear transformations iteratively to maximize reconstruction performance, and that's it. So it's way more direct, and it is nonlinear, so it probably performs better than PCA. So yeah, you can actually compare. You can actually implement PCA and autoencoder and compare the performance between the two. It usually, when you use small number of Ks, like 10 or 20, then autoencoders show better performance. But if you use like larger K, like when your input is 784, then your K is like 200. Then there's basically there's no difference between the performance of autoencoders performance of PCA, because now you're using 200 base, which is just probably more than enough to describe the data set. And the autoencoders can easily map to higher dimensional space, but PCAs you have to use something like you can use like kernel PCAs to map to higher dimensional space. The reason that I'm saying this is because it doesn't always have to be that your hidden dimension must be smaller than your input. It's the same principle. So there's nothing stopping you from using a larger dimensional space, which I don't see a reason why we should do this, because if you have a Z space which is larger than your X space, then you can just have a identity matrix that maps your entire thing to here, and then just zero all the way, and then maps identity again and zero all the way. That could be your latent space. But yeah, but theoretically you can do this. You can do this kind of weird thing. Okay. A lot of questions. Probably not today, so 설명해 줄 수 있을까요? Probably not. 요거 말씀하시는 것 같은데. 그러니까 제가 말씀드리고 싶은 거는 이렇게 열심히 4차원으로 축소를 했으면 그 4차원의 각 차원마다 무슨 우리가 해석할 수 있는 의미가 있을 거냐 이건데, 아마도 아닐 거란 아주 높은 확률로 99% 확률로 안 그럴 거다. 해석할 수 없는 차원이 나올 것이다라는 얘기입니다. PCA를 생각해보면 PCA에서 이렇게 제가 지금 보여드렸잖아요. 지금 이제 아파트 값이나 뭐 이런 데이터셋이 있을 때 그걸 이제 PCA를 해보면 PCA에 나오는 베이시스도 그것조차도 해석하기가 쉽지가 않은데, 이렇게 넌리니어한 오토엔코더를 쓰면은 나오는 그 넌리니어 스페이스는 해석하기 굉장히 어려울 거다라는 게 제 말씀입니다. 아이겐벡터 찾는 거라고 생각하면 네, 맞습니다. 아이겐벡터 찾는 거 맞습니다. 네. 그 코베런스 매트릭스의 아이겐벡터를 찾는 거랑 같은 얘기고, 그게 결국에는 원래 X의 아이겐벡터를 찾는 거랑 같은 얘기가 됩니다. X는 코딩 시키는 네, 아까 말씀드렸는데 방금 말씀드렸죠. 여기서 이제 만약 X가 이렇게 굉장히 익스트림한 밸류로 왔다 갔다 하면은 요거를 학습하기가 어려우니까 그걸 이제 다 맞춰주는 거예요. 다 이제 모든 차원을 같은 레인지에 있도록 0, 1로 맞춰주거나 1, 마이너스 1, 1로 맞춰주거나 그렇게 해야지 여기 다음에 올 웨이트 매트릭스가 일이 편해진다는 거예요. 이거 소정님이 엄청 끝에 있는 숫자까지 찾아봐야 돼서 비효율적입니다. 엄청 끝에 있는 숫자를 찾아본다는 게 그 의미를 잘 모르겠는데, 하여튼 뭔가 이게 레이트 스페이스 얘를 이제 얘를 이제 뭘로 보내서 나중에 이제 리그레션을 하든 클래시피케이션을 할 거잖아요. 근데 이게 만 뭐 0.001, 뭐 10, 마이너스 1, 마이너스 뭐 100만 이러면은 여기서 여기로 갈 때 배우는 이 W의 값들이 이걸 맞게 조정이 돼야 되는데 이게 지금 차이가 너무 많이 나니까 디멘션마다. 그래서 그 배우는 게 쉽지가 않다라는 말씀입니다. 아, 네. 네, 알겠습니다. Alright. Alright, so this is the end of the autoencoders, and we're moving on to training process. So if you have a question, please, you can use the chat box as usual. Just want to talk about the training process a little bit in detail because for the people who have never trained a neural network before. So basically your high-level process looks like this. So it's you first start by splitting your data set into training, validation, and test. So I'm trying to, you know, by telling you this, by teaching this section, I want everybody to be able to imagine how they want to code in their PyTorch in their PyTorch framework, how they would code or how they would implement their model and how they would train their model using this kind of canonical loop, basically. So the overall process is you start with splitting your data set into train data set, validation data set, test data set. You load the data, you define a model, and by defining a model, you're actually defining a loss as well, and then you define an optimizer, and then you put a training loop, and then you evaluate the best model and test it. So this is your high-level idea, how you want to compose or construct your entire training phase. We'll just go one by one. So splitting into a train, test, validation, test. So usually you want to split your data set into like 80 to 80, 10, 10, maybe 60, 20, 20, but that depends on the real world use case. So there's no like golden rule of what the best split is between train, dev, and test. And when you're splitting, you want to consider the possibility of doing n-fold cross-validation. So I said that in modern deep learning, people don't really do n-fold cross-validation when your data set is really huge. But in classical machine learning, you want to consider that. And you can use, as I said, you can use scikit-learn train test split. There's a utility function scikit-learn. So remember this. And then loading the data, you can either load your entire data into your memory or you can stream that from the disk. So there are two options basically. And if your data set is small enough that it'll fit into your entire physical memory, which is RAM basically, then you can just, read that from your disk and then load it onto your RAM and then use it to construct your mini benches. But if it's really large, if your data set doesn't fit into your memory, or is it streaming, or if it's streaming from a database, or video, or audio, then you need to use something called you need to stream that from the disk. So there should be like a file descriptor open or connected to your file in your disk, and then read it sequentially, basically. And there's a utility function in PyTorch that makes the job of this really easy. So it makes your life easy, way more comfortable. There's a utility function called dataset, and there's a utility function called data loader. And I won't go into detail what they are, but basically you've already used it in the previous practice section when you were classifying MDisk images, but I don't think the TA went into detail. But when you're not using MDisk, when you want to use your own data set to train your own neural network, you need to use dataset and data loader. And these combination supports both in-memory and streaming from the disk. So remember this, and there's like API documents on the internet when you go to pytorch.org, so you can look it up. And then defining a model. So defining a model, we already talked about the NN module. So you can inherit from the NN module class to define your model, and then by doing it, you also need to define your loss, which is either cross entropy, MSE, or it could involve regularization as well. So you need to define your loss L, and you can use torch and then a star like cross entropy loss or binary BCE loss or MSE or whatever. So, or you can define your own loss actually. So that won't be too difficult. So this part is actually just defining your model, which was really easy in the previous practice because we were using just two hidden layers. I think it was 1 or 2 hidden layers or something. So it was basically a feed forward neural network. So it didn't really take a lot of effort to define your model. But when you are in the like the second half of this course, we'll be implementing transformer from bottom up. So then that would involve a lot of effort. So once you've defined your model, you need to define your optimizer. And you can use either SGD, AdaGrid, AtomX. And they are all there in your PyTorch. There's a torch.optim package. Inside, there's a lot of different flavors of optimizer. You can just use that. I mean, if you want to do research on optimization, then you need to define your own. But other than that, I suggest that you use, already implemented optimizer. Don't try to implement your own optimizer. So that. So we've talked about this part, which is basically setting up. So we haven't really gone into the loop of training. This is just laying the groundwork to actually start your training loop. So once you've done that, once you've defined once you've loaded the data, defined your model, defined your loss, defined your optimizer, then you need to start your training loop, which looks like this. So the overall, there will be like the highest level repetition, which is for loop, over the number of epochs. So a single epoch is when you have gone through your entire data set. So you're doing mini-batch gradient descent. And for example, if your entire data set, X, is like 1 million, so this is 1 million by maybe 780 space. So it consists of 1 million is 10,000, 10K. So your data set consists of 10,000 examples of 784 dimensional input, and you want to break it down into like mini batches of maybe 100 samples per mini batch. Then how many iterations do you need to proceed in order to see the entire data set? That would be 100 iterations, right? If you're using batch size of 100, batch size 100, then you need to go through 100 iterations, which is equal to 1 epoch. So this is repeating n epochs. So how many times you want to see the entire data set? And then under the for loop, there's another for loop which goes through the mini batches. So this is like iterations. So repeat for k batches. In this example, it should be 100 batches. And then inside the batch for loop, you should fetch a random mini batch from your data set. It should be a random mini batch. There can't be dependencies between like previous mini batch and the next mini batch. Then that would destroy the principle of stochastic gradient descent. So you fetch a random mini batch, you push x through m, which is your model, and obtain y prime, calculate your loss, use O, the optimizer to update the model's parameters, and then you evaluate your model. Once you finish a single epoch, so this is single epoch, the entire loop goes for a single epoch. And then once you've done that, you want to evaluate your model on a validation set or a development set. And if the validation performance is the best one that you've seen so far, then you want to save your model's parameters somewhere else that you can reuse it in the future. So again, we'll go one line by one line. So for the epoch for loop, the iteration for loop, then there's fetch a random mini batch. And when you're fetching a random mini batch, you can implement that process by yourself, but I suggest that you use data loader as well. So when you use data, like torch utils data set and torch utils data loader, then it'll do a lot of heavy lifting for you. So you can just define like the size of the mini batch, how you want to shuffle it, and all that kind of like optional arguments. And then once you just enumerate over the data loader, then it'll just fetch a random mini batch from your entire sample for you. So it becomes like way easier to do a stochastic gradient descent. And your X will be like some batch number of samples, like batch size number of samples, so some batch size number of labels as well. So using data loader. And then you push your X through M. So basically just you have your model M and then you use model M as a function and then you put X through it and then you get Y prime. And all these will be actually mini batches of Ys, mini batches of Y prime, mini batches of X samples. You calculate the loss. I'm going to call the loss C, which is like short for cost. So, and you want to print your C or your loss every once in a while, so that to see if your model is learning, to see if your model's loss is decreasing, then it means that your model is training well. But if the loss is not decreasing at all, then it is not learning anything at all. Because as you remember, what we're doing in training a machine learning model is basically optimizing your loss function by controlling the parameters. And optimizing, I mean minimizing your loss function. So it needs to decrease for the optimization or the learning to happen actually. And then using optimizer to update the model's parameters. So you have the C, and then I hope you guys remember that you need to first call zero grad, and then use C, which is the loss backward, and then take the step, and that's it. So it's really easy in PyTorch. Like all these like complicated like steps of every single steps of training your neural network can be broken down, can be like boiled down into few dozens of lines of code. Right. So okay. So this is so far the first for loop, the second for loop, so the epoch for loop, the mini batch for loop, and then now we're left with, after we've got a single epoch, you want to evaluate your model on a validation set. And how it does is there's another for loop actually involved, because your validation set might also be bigger than your mini batch, or it might be bigger than your model can take in a single step. So you want to break it down into different mini batches as well. So even if you're just evaluating your model performance and validation set, you need to go through the same process again. And here you're doing for J batches of validation set. And this could be, so it doesn't necessarily have to be the case that the batch size in the training loop and the batch size in the validation performance evaluation loop, it doesn't need to be the same. All you need to do in validation set is just go over the entire validation set once and then calculate the validation performance, and that's it. So it doesn't have to be like both in here and here, they don't have to use the same batch size. But it needs to be some batch size that will, or you need to go through the number of iterations here, the number of iterations here needs to be such that you go over the entire validation set once. And you're fetching next mini batch. So you're not fetching random mini batch. You're fetching next mini batch. If this is your validation data set, then you're taking this much and this much and this much into like sequentially, so that you can go through the entire validation set. So fetch the next mini batch, and here you're using another data loader. So when you are defining data loaders here, you are actually this needs. This needs to be here and this needs to be here. So when you are defining your data loaders here, you need to define 3 different data loaders, which is train data loader, validation data loader, and test data loader. So here, before here we were using train data loader. Now we are using validation data loader. And then after that, it's all the same. You put your X through the model and obtain the Y prime, and then save the batch for. What you want to do with validation performance is you want to go through the entire validation set and then calculate the overall performance, which is accuracy or F1 score or BLUE score or AURC or precision recall, whatever metric that you want to use. You want to go through the entire validation set once and then calculate the final validation performance. So in order to do that, you need to save the intermediate performance somewhere else in another variable. So like this is whether your prediction is right or wrong. This is your MSV, whatever. Like basically, you need to save this information somewhere so that you can pull this all together and calculate the final AURC or MSC or accuracy. And if your validation performance is the best one so far, because you are calculating validation performance after every single epoch, right? So you'll be calculating a lot of validation performances. And in this specific loop, in this specific iteration, if your validation performance happens to be the best one so far, then you want to save your model somewhere else so that you can reuse it in the future. And the way you can save it is just copying state things. State dictionary is where your model parameters are saved. So you want to save your model parameter, or you can save it locally in your hard drive. So you can use either approaches. But basically, note that you need to save this value, state it. Right, and then after you have after you've completed your training loop, then you want to, for the last step, you want to evaluate your best model so far on the test set to calculate test error or test performance. It's the same thing. So you load before you evaluate your test performance, you need to load your best M, which is this. So you saved your model state dict somewhere, right? You saved your state dict somewhere, maybe locally in your hard drive, or maybe just as a variable. You saved it somewhere, and then you need to load it in your model again. So you've already defined your model. By loading state dict, you're actually loading the learned parameters from somewhere else, and then you can actually directly load it, or you can load it from your hard drive. So load the best M, and then the rest is exactly the same as evaluating validation performance. You repeat for T batches of test set. You are using test data loader here. You push X through N, obtain the Y prime, save the intermediate prediction errors or MSE errors, and then calculate the final test performance, accuracy, accuracy, whatever you want. So this is the entire training process. So you start from the beginning until the end. Again, this should be here. This should be here. So you start by splitting the dataset, loading the dataset using dataset utils in PyTorch, and then you define a model by inheriting from NN module. You define an optimizer using torch.optim.star. You start the training loop, which there's like epoch loop, there's iteration loop, and then you load the mini batch, push X through M, get the loss, optimize, and then you repeat that again for the entire single epoch. Then you calculate the validation performance, and then after that you save your validation performance if it's the best one out so far. Then you move on to test, and you repeat that for like n number of epochs. And after that, you take the best one, and then you calculate the test performance, and that concludes your training neural network training entire procedure. Yeah, it seems complicated, but it's not really that complicated because there's a lot of repetition. Once you familiarize yourself with the training loops, like over the epoch, over the iterations, fetching the mini batch element, afterwards it's just repetition. You do that for a training data set, you do that for a validation data set, you do that for the test data set, and then you repeat that again and again and again and again. All right. Hope this is pretty clear. We only have 6 minutes left, which is unfortunate. A lot of. Okay, I can't answer all these questions. I'll go through that after the class, and then hopefully if there's something that I can answer, then I'll answer that on class. All right, visualization. So once you have learned your latent representation, once you've compressed your data into a lower dimensional space, then hopefully, assume that you're compressing your MNIST images, hopefully these two, which are ones, the latent representation of them, this and this, should be similar, more similar than this pair, which is 1, 5. So that is the proper latent representation, because semantically they're the same thing. They're 1, this is 1, this is 5. So, and just going pair by pair to see if your latent representation is well structured or if your latent space is well learned. Going calculating similarity between all the pairs of n pairs, which takes n squared, is probably a bad idea. So you want to visualize it like this. So it's easier to draw on a 2D plane. So, all the dots here, dot here, they're all individual samples in your MNIST images. And the pink ones here are all 6s, The green ones here are all 2s, orange ones are all 1s. So you can see that they're not that bad. I mean, it's not as like clearly like all the like. Ideally, what we want to see is like all the 1s here, all the 2s here, all the 3s here. Maybe 7 like here, because 7s and 1s might look a bit similar, like this. I mean, we want our space to be as like clearly distinctive, like clearly separable as much as possible. But here, this is okay, I guess. It's not that bad. But basically, you can like drawing on a 2D plane is way easier than just calculating pair by pair to see how your latent space is doing. So we need an additional dimension reduction step here, because what we did before is we had 784 compressed into 4-dimensional space. In 4-dimensional space, this is still not plottable on 2D plane, because there's no way you can draw a 4-dimensional space in your 3D world. So you need to downsize this again to 2D, to the 2-dimensional space only for visualization performance. So here, this is compression, maximize for reconstruction purposes. To compression to maximize reconstruction. I'm just going to recon. Here, I would say compressed. Yeah, this is also another compressed to maximize visualization. So they serve different purposes. So when you compress the original one to 4-dimensional space, this is what you will be using in your downstream test, whether you do clustering, whether you do regression, classification. This 4-dimensional thing is what you want to use. But when you want to visualize the 4-dimensional compressed input, you want to downsize it again to 2-dimensional space. So from dim-z to 4, which is dim-z to 2, where in our case it's 4 to 2, so that we can plane on 2D. And basically, there are 3 very popular algorithms for visualization purposes, which is PCA, t-SNE, and UMAP. And the 3 have slightly different purposes. So PCA is it's variance based. So, and it is already implemented in scikit-learn, so you can just call scikit-learn, call PCA, and then just reduce it to 2-dimensional space. t-SNE is distance based. So distance based, I mean, you calculate distance between the pairs of samples, pairs of your input samples, which is 4-dimensional space, and 4-dimensional input in our case, because we've compressed it down to 4, and then we're downsizing that to 2. So in this case, you're calculating distance, which is basically x minus x1 minus 2. So, or maybe it's just L2 or L2 distance. So this is distance space as well. This is variance space, covariance space. So t-SNE serves a little bit of different purposes, and it is it is implemented in scikit-learn, so you can just call scikit-learn, call t-SNE, and then try to see how it goes. Basically, t-SNE is it is assumed to be a better visualization algorithm compared to PCA, because what t-SNE does is, if something is similar, if your x1, x2 is similar, then it compresses your x into a 2-dimensional space to preserve the similarity in the higher dimensional space. So if something when you're compressing 4 to 2 using t-SNE, if something was similar, if something was closer, if some pair was closer in the 4-dimensional space, it still needs to be closer in the 2-dimensional space. That's what t-SNE does. So it preserves the closeness or the local neighborhood in the lower dimensional space. UMAP is basically serving the same purpose, but it's told to people say that it preserves global structure as well. So here in t-SNE, everything was local, because if something was locally close in the higher dimensional space, it still needs to be locally close in the 2-dimensional space. In UMAP, that purpose is still preserved, but it also respects the global structure as well. So it's like a hybrid version. And unfortunately, you need to explicitly install on your hard drive in your local computer but it depends on scikit-learn. So the syntax is exactly the same. Like if you use tsne in scikit-learn, you can use the same syntax in using UMap in scikit-learn. It's just that you need extra step of installation. And I think people like UMap a lot these days. So tsne was proposed like way back in maybe 2012 or 2014, like really long time ago. UMap was proposed in 2018, so it's a rather new algorithm. So let me, as a last step, let me just show you guys the difference between the two. Right, so what we are seeing is the clustering output of the fashion MNIST. There's a data set called fashion MNIST. So there's like images of pants, images of like your shoes, images of your shirts, images of dresses, just like images of 1, 2, 3, 4, 5. So there's fashion MNIST, and left side is UMap, right side is tsne, and UMap is a bit more, the clusters are looking nicer than tsne. And interestingly, your sneaker and your ankle boot, here, your sneakers and your anchor boot, these are all anchor boot, or oh, these are sandals. Okay, these are sandals, and your ankle boot are clustered in a similar region, like here. Compared to tsne, I mean, tsne is still there in the vicinity, but it's not as clearly distinctive as UMap. So I think UMap can be a nice alternative to tsne. Right, moving on. We're already past 12 o'clock, so if you guys have any extra schedule, you can leave, but this won't take a lot of time, maybe 5 or 10 minutes, so I'll just go through it. So autoencoders, I said we'll be learning denoising autoencoders, sparse autoencoders. We'll start with the sparse one. So sparse autoencoder is basically inducing sparse latent representation. So before it was like continuous valued 4-dimensional space. Now, typically in sparse autoencoders, you use larger like hidden space compared to before. So if your input is 4, then maybe your hidden dimension would be 8, but you only want a small portion of your latent space to be active. Active meaning non-zero. So like this is all 0, this is all 0, this is all 0. Only 2 elements in your latent space is active. So you want to induce this, you want to encourage this kind of behavior because it performs better in downstream classification tests. So once you've learned this kind of like sparse representation Z, then you can use that Z for like classification tests in the downstream. So how do we induce this kind of behavior? How do we encourage this kind of like sparse representation? Basically, you just add one more term in your loss function. So your loss function here is L plus omega, I would say. Yeah, loss function is L plus omega, and you still need the reconstruction loss, which is the essence of autoencoder. And then you need to have a sparsity inducing term omega, which is the added term to encourage this kind of like sparse behavior. There are basically 2 options, which is using KL divergence and L1 regularization. Yeah, I won't go into derivation, but basically the high level idea is you have the average activation value for each Z here, Z1, Z2, Z3, Z4. Like you can, once you have like a mini batch, you can calculate the average value of your Z1 and Z2 and Z3. That becomes your average activation value. That becomes your rho het I, and your rho is the target activation value, which is basically Bernoulli distribution mean, because it is either activated or it's not activated, 0 or 1, right? So you want to have a target Bernoulli distribution mean, which should be really low, like we should be like 0.01, maybe 0.1 or 0.001. Like if you use a very small value for your rho, and then do a KL divergence between your target and your empirical, your sample mean, then and you do KL divergence, then you're encouraging your activation values to be like really like sparse. So basically, like if you put this here like 0.01, then you want out of 100 times you only want once each dimension to be have an active value, something like that. And if you use 0.1 for the row, then and when you use scale divergence, then you're encouraging each dimension to be active every once in 10 times, something like this, because we're assuming Bernoulli distribution. All right, there's a lot of questions. Yeah, maybe I can address them after this class. All right, another strategy for encouraging a sparse representation is just basically using L1 regularization. So L1 regularization, if you're familiar with like lasso regression, that type of thing, if you use this kind of L1 regularization, then it is likely that your one of the z, so there are like I number of z, there's like this 8 number of z's here, so maybe maybe few of your z's in your 8-dimensional space would go to 0 a lot of times. Yeah, there's a lot of things that I can talk about regularization, but maybe another time. We're running out of time here. Okay, so that ends up the sparse autoencoder. We won't actually use sparse autoencoders a lot. This is kind of like an old concept. I don't think anybody uses sparse autoencoders that often these days. But it's an important model in the history of autoencoders. So we just took a look at it. Denoising autoencoder. This one we will implement in the practice session this Thursday. The principle is really simple. You just corrupt your input x to x tilde by adding Gaussian noise, and then you want to reconstruct based on your corrupted input, and that's it. So reconstructed input with random noise, or we call it a corrupted input. And the basic assumption or the principle behind this denoising autoencoder is that small noise doesn't affect high-level representation. So even if we have a lot of white noise here, we can still kind of see that this is digit 2. So that kind of like small noise or small variance doesn't really affect the true nature of your high-level representation. So that's okay. And you want your autoencoder to learn useful patterns to perform denoising. So in order to send this, compress it, and then decompress it, and then get a clear output, you need to learn useful features from this this corrupted input. So it's like, so once you've done this, then your denoising autoencoder can be more robust to real world data, or maybe it has better generalization performance. Yep, so small noise doesn't affect high level representation. This reminds you of something. Small noise is actually small variance. So small variance doesn't affect high level representation. This is actually the principle behind using small number of Ks in PCA. Because PCA, you want to preserve large variances first and then ignore the small variances, right? So that is the same thing as saying small noise doesn't affect high level representation. So it's all connected. All right, so the important thing is that loss function is not between x tilde and x prime. The loss function is x between x and x prime, which is the original uncorrupted input and your reconstructed output. So you don't want your autoencoder to reconstruct a corrupted input. That won't be really useful. You want to denoise it, right? So that's why it's called denoising autoencoder. So remember that this is your loss function, and corruption is usually done by adding Gaussian noise. So here, like there's like white. There's like gray pixels and white pixels added to your image of digit 2. So that is because you're using Gaussian noise to add noise to make your corrupted input. So that's it. So you can kind of see that the denoising autoencoder is very similar to PCA. So or singular value decomposition in that manner, because when you do singular value decomposition and you use the larger singular values to factorize it to lower dimensional space, that actually kind of acts like a denoising module for your image, which I guess that's more related to linear algebra. But it's like all these are very related to each other. All right, yeah, that's it. All right, so in the practice session this Thursday, we'll be implementing autoencoders, and then train it and then visualize it using t-SNE on two-dimensional space. So this visualization was actually borrowed from what we will be doing this Thursday. So we'll do visualization, and after that, we'll modify the autoencoder that you guys built into make it into a denoising autoencoder and see how it performs. So that will be the content for this Thursday. All right, thank you very much. I'll just go through the questions one by one and see if I can answer anything. Thank you. 감사합니다. 혹시 질문 있으신가요? 여기 분들 항상 질문이 없으시더라고요. 잘 이해가 되시는 거죠? 설마 이해가 안 돼서 질문 안 하시는 건 아니겠죠? 엄청 기네. 공기 입폭 중에 가장 로스가 작은 파라미터를 선택하는 건가요? 네, 맞습니다. 로스가 가장 작은 파라미터를 선택하는 게 아니라 밸리데이션 퍼포먼스가 작은 파라미터를 선택하는 게 보통 더 일반적이에요. 그러니까 트레이닝 셋에 대해서 로스가 작으면 그건 오버피팅할 가능성이 있기 때문에, 그러니까 트레이닝 셋은 이론적으로 아주 큰 모델을 쓰면 로스를 빵에 가깝게 막 보낼 수가 있거든요. 근데 그건 오버피팅이니까 보통 이제 별개의 밸리데이션 셋을 두고 거기에 대해서 가끔씩 이렇게 퍼포먼스를 측정한 다음에 그런 밸리데이션 퍼포먼스가 좋으면은 그거를 저장해뒀다가 나중에 쓰는 겁니다. 네, 폭이 진행된 건지. 폭이 진행될 때마다 이게 사실 아까 보여드린 이 룹에서 여기서 사실 요거는 여기는 없어도 돼요. 이건 없어도 되고 그냥 이 배치의 개수를 이거를 이 for loop을 한 뭐 100만 번, 1000만 번 이렇게 돌리면은 이 폭을 여러 번 돌리는 건 같은 효과가 납니다. 그냥 단지 이 폭이랑 이 폭 for loop이랑 이 배치 for loop을 놔둬놓은 거는 이 내 데이터셋을 총 몇 번을 볼지를 컨트롤하고 싶어서 그런 거거든요. 근데 그게 아니라 그냥 그 이 폭이라는 개념을 따로 안 두고 그냥 이 배치를 계속 여러 번 무한번 돌리면 랜덤하게 계속 샘플에서 또 돌리고 샘플에서 또 돌리고 샘플에서 또 돌리고 이렇게 하면은 그게 결국은 이 폭을 여러 번 보는 건 같거든요. 그래서 실제 학습은 여기서 일어납니다. 여기서 이제 배치를 랜덤 배치를 뽑아가지고 그거 가지고 학습을 하는 거가 여기고 그거를 그냥 상위 개념으로 이 폭이라는 걸 더 쓸 뿐이에요. 그냥 이거를 아주 오래 하면은 이 폭 여러 번 돌리는 거랑 같은 효과입니다. 네, 그게 명지윤님에 대한 질문에 대한 답이었고, 예, 재균님이 그 답을 해주셨네요. 이 폭이 반복될 때마다 파라미터 최적화되는 것인가요? 이 폭이 반복될 때마다 파라미터 최적화되는 게 아니라 배치 한 번에 대해서 학습을 할 때 그때마다 파라미터 업데이트가 일어납니다. 미니 배치 스토캐스틱 그레디언트 디센트이기 때문에 미니 배치 하나 가지고 y 프라임 얻은 다음에 로스 칼큘레이트 해가지고 업데이트 할 때는 m의 전체를 모든 파라미터 업데이트하는 거예요. 그러니까 이 폭마다 업데이트가 되는 게 아니라 이 배치 이터레이션마다 업데이트가 되는 겁니다. 네, 신현호님 말씀이 맞습니다. 명지은 최적화되는 것은 n번 이퍼는데 마지막. 최적화되는 거는 n번 이폭을 돈 뒤에 마지막 파라미터를 선택하는 걸 말한 건데 중간에 가장 좋았던 파라미터를 선택한다는 말씀이시죠? 네, 맞습니다. 근데 방금 말씀드렸듯이 사실 이 이폭 룩은 없어도 되기 때문에 그냥 이거를 100만 번, 1000만 번 돌리고 배치 이터레이션. 근데 예를 들어서 100번에 한 번씩 밸리데이션 퍼포먼스를 측정한다. 1000번에 한 번씩 밸리데이션 퍼포먼스 측정한다. 그런 식으로 하셔도 돼요. 근데 요거를 이게 그냥 캐노니컬하게 사람들이 많이 쓰는 방식이기 때문에 이렇게 한 거지 꼭 이렇게 무조건 이 폭이랑 이 배치를 나눌 필요는 없습니다. 파라미터 모델을 선택적으로 저장하는 맞습니다. 가장 베스트 이폭 모델을 저장하는 것입니다. 네. each epoch is equal to performing iterations on the entire training data set and equal to mini batch set. The entire data set equal to what? Each epoch is equal to performing iterations on the entire training set and equal to mini batch set. Rushda, I don't think that's what I meant. So each epoch is in your second for loop. That's when you use mini batch to update your parameter, the model parameters, and you repeat that as many times as required to go through the entire data set once, and that completes your single epoch. So that's that. Yeah. 로스 출력에서 학습이 잘 된 적이 일어나는데 밸리데이션 스포츠는 그것과 다른 거예요. 네, 그건 다른 겁니다. 그렇지. 이 로스 출력하는 거는 여기 이 로스 출력하는 거는 트레이닝 데이터셋에 대해서 학습이 잘 되고 있는지를 보려고 하는 거예요. 그러니까 이 로스는 트레이닝 로스예요. 트레이닝 로스. 그러니까 이거 한번 미니 배치를 가지고 업데이트 할 때마다 로스가 발생하기 때문에 그 로스를 찍어보면은 전반적으로 로스가 줄어드는지를 볼 수 있고 전반적으로 로스가 줄어들어야지 모델이 적어도 트레이닝 데이터셋에 대해서 학습이 되고 있다는 걸 확인할 수 있습니다. 그거 외에 밸리데이션 테스트 퍼포먼스는 로스가 준다, 트레이닝 로스가 준다 그래서 완전 땡이 아니라 왜냐면 오버피팅 할 수 있기 때문에 중간중간에 가끔씩 밸리데이션 데이터셋에 대해서 모델의 성능을 측정을 해보는데 그때 그냥 로스를 쓰는 게 아니라 아이큐러시나 이런 대체제를 쓸 수가 있다는 얘기예요. 그래서 이 트레이닝 로스랑 밸리데이션 퍼포먼스랑 다른 얘기입니다. 제가 따로 주장하자는 자동 테스트 모델 아닙니다. 이거 직접 하셔야 돼요. 여기 보셨죠? 여기 보셨죠? if best validation performance 이거 if문 쓰셔야 됩니다. if문 쓰셔야 직접 저장하셔야 돼요. 학습은 백워드가 호출될 때 된다. 백워드 호출될 때 학습되는 거 아닙니다. 주윤상님 백워드를 호출할 때는 백프라고로 그레디언트만 계산해 놓는 거예요. 각 웨이트마다 각 파라미터마다 그 그레디언트만 계산하는 거고 이거죠. 이것만 열심히 계산하는 거고 백워드는 이게 백워드고 옵티마이저로 스텝을 해줘야지 그때 업데이트 일어나는 거예요. 스텝 안 하면 업데이트 안 일어납니다. 최고의 밸리데이션 액큐레이션한 F 모델을 저장한다고 생각하시는데 그건 맞습니다. 네. 저장이 저절로 되는 건 아니고 네, 직접 해줘야 돼요. 예를 들어 100개의 데이터를 20개의 페이지 사이즈로 나누면 이터레이션은 5가 되고 5번은 이터레이션 잘 되고 이렇게 보입니다. 즉 100인 폭을 돌다 90번째 일폭에서 네, 아주 정확합니다. 이종민님. 그 말씀 맞습니다. 네, 저는 이 폭이 오면 5폭을 도는 게 써야 됩니다. 네, 명지훈님 그거 아니에요. 교수님 멀티디멘션 피처랑 반영됐을 때의 데이터 분포를 비교하고 싶어서 티스를 볼 때 샘플 중 클러스터링 되어 있지 않고 다른 한쪽으로 찍히는 샘플 부분을 아웃라이어로 제거하는 게 나온 방향인가요? 이 티스니가 진짜 중요한 게 있는데 시간이 없어서 넘어갔는데 티스니는 이 티스니랑 유맵은 둘 다 로컬 디스턴스 between pairs of samples preserved. 둘 다 이거가 기본이에요. 이거가. 그러니까 로컬 디스턴스만 보존을 하기 때문에 그러니까 이제 원래 원 차원에서 로컬 디스턴스가 있었고 그 다음에 줄인 차원에서 로컬 디스턴스가 있는데 그 두 개가 로컬 디스턴스가 비슷해야 된다는 게 티스니와 유맵의 기본 정신이거든요. 그렇기 때문에 이 어느 한 이 클러스터가 예를 들어서 아까 클러스터가 이렇게 생겼다고 그래서 여기서 이 보라색 있잖아요. 얘네 이제 바지들 있잖아요. 바지들이랑 신발들이랑 지금 멀잖아요. 거리가 신발들의 거리가 멀잖아요. 이 거리가 멀다고 해서 정말로 바지랑 신발의 거리가 먼 게 아닙니다. 절대 그런 거 아니에요. 로컬 디스턴스만 보존하기 때문에 여기 있는 애들이 서로 비슷한 건 맞아요. 이 신발이랑 앵클 부트랑 스니커즈랑 무슨 샌들이랑 얘네들이 같은 비슷하기 때문에 거기 맵핑된 건 맞는데 이 팬츠, 이 바지들이랑 신발이 멀다고 해서 정말로 그 멀다는 건 보장이 안 돼요. 그러니까 글로벌 스트럭처는 100% 보장이 되지 않습니다. 티스닝 그게 더 심하고 그렇기 때문에 클러스터가 멀리 있다고 해서 아웃라이어가 절대 아닙니다. 그거 아니에요. 네, 성진님 질문하셨구나. 네. 아니, 동명이 있으실 수도 있는데 하여튼간 네, 성진님 그거 아닙니다. 네, 아웃라이어 제거하는 거 아니에요. When does denoising autoencoder perform better than vanilla autoencoder? 전반적으로 denoising encoder가 거의 항상 바닐라 autoencoder보다 잘 된다고 보시면 돼요. 저 손해볼 건 없다라고 생각하시면 됩니다. 근데 사실 뭐 항상 그런 거 아닌데 어쨌든 뭐 써서 나쁠 건 없어요. 기본적으로. Rushda, how does sparse Autoencoder use Bernoulli distribution in? Right here. So you're assuming that the activation of your hidden representation Z is either 0 or 1, so which means that it is a Bernoulli distribution. It's binary distribution. It's either 0 or 1. It's either active or it is inactive. So that's why you want to model your Z as a Bernoulli distribution and follow a target distribution mean, which is, as I said, could be 0.01 or 0.1, depending on how often you want each of your Z dimension to be active. And enforcing that is by using KL divergence between the target mean and your empirical mean. I hope that makes sense. PCA와 오토엔코더 비교 시 K값이 작을 때 오토엔코더 좋다고 하신지를 설명해 줄 수 있을까요? 그게 그 PCA는 K값이 작으면은 그 막 다이렉트리 베리언스를 버리는 거랑 똑같거든요. 근데 오토엔코더는 베리언스를 버리는 개념이 아니라 리컨스트럭션을 맥시마이즈 하기 위해서 4디멘션이든 몇 디멘션이든 다 갖다 쓰는 거기 때문에 두 개가 조금 기본적으로 차이가 있어요. 원천적으로. 네. 그러니까 PCA를 쓸 때 뭐 하나만 쓴다, 두 개만 쓴다, 제일 큰 아이겐밸류 쓴다, 뭐 아이겐밸류 2개 쓴다. 이거는 어떤 말이냐면은 베리언스가 제일 큰 베이시스 하나를 쓴다, 베리언스가 제일 큰 베이시스 2개 쓴다 이런 얘기거든요. 그렇기 때문에 조금 쓰면은 그만큼 정보를 많이 잃어버리는데 오토엔코더는 애초에 우리가 4디멘션, 6디멘션 Z를 설정할 때 베리언스를 버리는 개념이 아니라 리컨스트럭션 맥시마이즈 하기 위해서 거기 N디멘션 다 이렇게 패킹을 하는 거기 때문에 학습의 그 애초에 목적이 달라가지고 K값이 작을 때는 오토엔코더를 쓰는 게 더 이득이, 전반적으로 이득입니다. 교수님 강의 전에서 비주얼라이즈를 위해서 4D에서 2D를 줄였는데 2D를 줄이기 전에 엄청 큰 차원이라도 가능. 네, 맞습니다. 사실 우리가 4D에서 2D를 줄였는데 그게 아니라 T순위를 여기서 처음부터 784차원을 처음부터 78. 네, 처음부터 784차원을 처음부터 2로 T순위든 뭐 U맵이든 이용해서 줄일 수 있어요. 사실 중간에 굳이 이 오토엔코더를 껴가지고 그걸 뭐 4든 8이든 줄이고 다시 그걸 2로 줄일 필요는 없고 그냥 순전히 비주얼라이제이션만에 관심이 있다 그러면은 그냥 처음부터 바로 원 차원에서 T순위나 PC 뭐 U맵이나 이런 거 이용해서 2차원을 줄여도 됩니다. 네, 동명이님. 네, 알겠습니다. 네, 그러면 질문 다 답을 한 것 같네요. 네, 감사합니다. 더 이상 질문 없으면 오늘 이 정도로 끝낼게요. 네, 감사합니다.
감사합니다.
네, 감사합니다.